Good. Good.
Okay. Welcome, everybody. Happy Tuesday. Thanks for coming to our seminar today. We'll be welcoming Dr. Sarah Ringerud to discuss her her research on global precipitation measurement. You want to come on up? Oh, but first she's going to be introduced by Ralph Ferraro. Apologies.
Yeah, hi, everybody. Thanks for coming. I think we have more here than we had for the all hands meeting. So Sarah knows how to fill the room for us. Looking forward to Sarah's talk. Sarah, I've known Sarah for a long time when she was a student at Colorado State. I don't know, I think Velko, you were there too, met at some meeting, which probably got you doing what you're doing today. And Sarah then she graduated at Colorado State, master's PhD prior to that at Wisconsin, and then did a postdoc at Goddard, and then she worked here for several years before she landed nice position at Goddard. So it's a nice, big loss for us, but a gain for Goddard. But it's a nice career path that we like to see people take. So now you're the deputy scientist, project scientist for the GPM mission, and she's going to give us an update on that. So welcome, Sarah.
Thanks for that. First of all, it's fantastic to be back here at ESSEC. I really valued my time at ESSEC, and I continue to highly value my colleagues here who I still work with very closely. So thanks for the invitation. I appreciate it. I have spent much of my career in this rather esoteric world of algorithm development. And algorithm development doesn't make for the most entertaining seminars. It's a lot of like math and computer programming. So I decided for this talk to kind of broaden it out to talk about, global precipitation measurement in general from satellites, sort of the state, where are we now? And also some insights into current challenges and where I think things might be heading in the future. And along that path, I'm going to really focus in on a few very specific things, and I'm also going to completely not mention other things. And you're probably going to be wondering, why is she spending so much time on this particular topic? And the answer to that question is because that's what I have found interesting and spent time working on. So it's my seminar, and I can talk about whatever I want. So with apologies to whoever invented this meme, I thought we'd begin with how it started. So this is a photograph from the Tyros-1 satellite on May 16th of 1960, as reproduced in a paper in 1961. And the authors of this paper were very excited to have matched the bright white clouds that they saw in this image with surface weather reports of severe weather. So some of the first work connecting what they were seeing from space with weather on the ground. So May 1960. And then this is how it's going. So this is from last week. This is a GPM animation starting here with I-merge precipitation of what was then Tropical Storm Milton, churning away in the Gulf of Mexico. And as we zoom in here, this was an overpass by the GPM-Core Observatory. And so you can see we have the 2D information from the wide radiometer swath, but we zoom in to see this beautiful 3D information from the GPM radar. The light colors there are liquid precipitation, the blue are ice at the top of the clouds, and you can see we get this amazing 3D understanding of what's happening inside this rapidly intensifying tropical storm. So quite a journey from 1960 and that photographic image to what we're seeing here. From GPM. It's, it was instantaneous overpass from the core satellite. Yeah. And then the precipitation you were seeing was from I-merge, so that was half hourly. So just a quick word about why we're doing this from satellites. I think everyone in this room probably knows the answer to this question. But precipitation is highly impactful to all of us on the Earth. And on a global scale, it's extremely important if we want to understand the global water and energy cycles because of the latent heat component of that. And gauge and radar coverage, as we know, is very sparse on the global scale. On the right, I have a figure here from Essex own Chris Kidd, showing the distance to the nearest GPCC rainfall gauge. So you can see we have a higher concentration in the populated areas, but wide areas where it's pretty far to see a gauge. And of course, the oceans where we basically have nothing. And particularly if we want to understand the global scale for those energy and water budgets, we really need that ocean coverage. And for climate monitoring, global long-term coverage is really what we need to be able to even start talking about putting these kind of observations into the climate realm. So I want to do a little bit of history on these microwave observations. So in the 1970s, it was primarily visible and infrared empirical techniques relating cloud top temperatures to surface observations of rainfall. And then in the 80s, they start planning for this microwave mission by the Defense Department, SSMI. And this is a figure from a paper by Tom Wilhite and many others in 1982. And this figure is from an airborne radiometer that they were flying at multiple frequencies. The frequencies are listed in the table on the bottom. But if you look at A, the bottom figure here, this one is 92 gigahertz. And if you look at E, which is the top line, that's 19 gigahertz. So we start to see that they're able to measure and look at what we know from theory, which is that in the lower microwave frequencies, they're going through, I should have said, a tropical storm here, tropical storm Cora. When you see precipitation, and particularly heavy precipitation, like associated with a tropical storm that has an ice component at the top of the cloud, you're going to get emission at the lower frequencies that you can see, so a warm emission signal from the liquid water. And then from the ice particles at the top of the clouds, you see a dip in the brightness temperatures where you're getting a cold scattering signal from scattering by ice particles. So the combination of these, even just two frequencies, can tell you something really interesting about precipitation. And that's another order of complexity above just a simple infrared cloud top temperature to rainfall. You know, you're seeing something about the liquid and something about the ice. So things really start to get interesting when they start looking at the microwave. And this is a paper from 1992. Guosheng Liu led this study, and here things are ramping up with the Global Precipitation and Climatology Project is being proposed as a 10-year, 2.5-degree global data set of monthly rainfall. So that's kind of the scale we're working at here. And this is a figure from this 1992 paper that Guosheng wrote, where they're really starting to quantify now these empirical relationships. So if you look at the y-axis, they're differencing the 19 and 85 gigahertz and using those relationships to come up with a quantitative rain rate. Again, using that combination of the warm emission signal from liquid and the cold scattering signal from the ice. Okay, now fast forwarding to 1997, we have the launch of the Tropical Rainfall Measuring Mission. So this is the first really precipitation-focused satellite. And the observatory sketch is from Simpson et al. 1996, is shown in the top there. And what's really exciting about this is it has a coincident active sensor from the precipitation radar and a passive microwave radiometer. So this is like an amazing combination of all these different types of information content coming together specifically to look at tropical, in this case, precipitation. It was a joint mission between Japan and the United States, again, focused on the tropics. But what was really exciting was getting the active and passive together, and also had visible IR instrument. And this was a long-lived, amazing mission. You can see these rainfall maps on the right. So we start to see these global maps. It went from 1997 to 2015. And we start to see more of these multi-satellite type analyses. So this is from a paper on the TRIM multi-satellite precipitation analysis, or TMPA. And they're showing here the swaths of all these different radiometers that they're using to come up with their global measurements. GPCP is moving now to a finer scale. And TMPA has a 1/4 degree 3-hourly resolution here. They have 2 different products, a real-time and a research product. And in the research product, they start to incorporate gauges. So really working on bringing together all of the available information to make the best possible global product, quasi-global in this case. And then we get to the launch in 2014 of the follow-on, which was the Global Precipitation Measurement Mission. It is 10 years in orbit and still going strong. We recently boosted the orbit, so hope to have it flying where it is until about 2030, and then still collecting data as it drifts down for the next couple of years after that. So we sort of add on another layer of information content with GPM. First of all, we have a 65-degree inclination now, so we're getting a lot of that mid-latitude precipitation that we weren't able to see, and even higher latitude. We still, sort of centerpiece of this is the core observatory, which has the coincident, active, and passive information, which is really key. But we've added information. So the active sensor now is dual frequency in the KU and KA bands. And the radiometer has 13 channels. So we're getting a lot of this information. And then what started with TMPA and TRIM and was really fleshed out in the GPM mission is this idea of a constellation. So when we talk about GPM, we're not just talking about the core observatory. We're talking about the application and use of that core observatory as a calibrator to bring in this huge constellation of what we call radiometers of opportunity. So basically, any radiometer that we can get access to. And we have a lot of global partners in this, particularly Japan and the European Union. But we will take in any of those radiometers and by using the core satellite as a calibrator, develop consistent precipitation retrievals from each of those, which have, different footprint sizes, different frequencies, different viewing geometry. We try and do something consistent about all of those to stitch together into a global product. And on the right here is an example of just a snapshot of one blended global product view. So you can see the GMI is a thinner swath, and it has this inclined orbit. And then we have all of the polar orbiters contributing information, again, at those different frequencies. So I wanted to say a little bit about how the flow works to connect all of these algorithms and make a consistent global product. So kind of the centerpiece of GPM is called the combined retrieval, to be combined, or people will refer to it as CORA. And basically, it's using all of the available information from the core satellite to make the best possible retrieval. So both frequencies of the active, all of the frequencies of the passive, and coming up with the optimal solution given all of those information. Those retrievals then become a transfer standard that's applied across the constellation, again, for that consistency. But as you noticed from the map before, the bulk of the information into any snapshot of global rainfall is coming from those passive microwave instruments. For those, we use the Goddard profiling or GPROF algorithm operationally. It uses a database constructed from those combined retrievals. So that's kind of how it's calibrating there. And then until now has used a constrained Bayesian retrieval. A Bayesian retrieval constrained by TPW, 2-meter temperature, and surface type coming from model information. This is moving to a machine learning operator. However, the database is the same. So still using the same basic information to retrieve, just with a different operator. iMerge then is the multi-satellite global product. It's an integrated product every 30 minutes. It takes in all of those passive radiometers from the constellation. It also uses gauges and morphing and intercalibrates everything again to those combined retrievals. So the combined really are sort of the passkey that leads to this consistent global product. And this is all done I'm sure you can tell from the description, this requires a lot of man hours and processing and money. So this is, we have the precipitation processing system, which brings all this together and runs all the algorithms, downloads all of the data, et cetera, et cetera. And this is the result. So this is GPM iMerge, the half-hourly product from last week. So obviously a lot of exciting things happening in the Gulf of Mexico and tropical Atlantic, but I love staring at these weekly animations and just seeing the mid-latitude cyclones go by in the northern and southern hemisphere. I just think they're beautiful. And the way we get this picture and the way it doesn't look like a patched together quilt or a Frankenstein is by using this calibrator to make consistent retrievals, and we get this beautiful animation. iMerge is by far our most popular product. It's downloaded orders of magnitude more than anything else we have at the PPS. And it's used for many different applications. Obviously, a lot of science. If you go onto Google Scholar and search precipitation, you'll see that a lot of those studies are using iMerge data. It's also used in data assimilation and numerical weather prediction. It's used for tropical cyclone monitoring. It's also used for things like deciding where cholera vaccines should be sent based on recent precipitation. Very valuable for many, many different applications. So what do we need? What are the ingredients we need to put this together and to do it well? So we need the sensors. They need to have the appropriate information content. We need to know about that emission. We need to know about that scattering. We need the right frequencies and the right resolution. It has to be somewhat on the scale of the precipitation properties that we want to look at. As I've said a couple of times already, the backbone of this product is those passive microwave observations. So they are extremely important. We need the correct sampling. So, it's really important that we have something in inclined orbit so we can see the full diurnal cycle from the calibrating sensor. And then we need coverage in all of the times of day from the polar orbiters too, to be able to get that full global picture. So we need the right sampling and configuration of the constellation. It needs to be calibrated for this to be a consistent product. And that has both, calibrated in a hardware sense and a software sense. So the radiometers themselves need to be calibrated. And we have a team at GPM called XCal that focuses on that. And they make a product called Level 1C that gives you brightness temperatures for each of the constellation members, all calibrated to GMI. And then there's a software calibration component that happens in creating the global product as well, where the iMerge team uses the to-be combined product to calibrate all of the rain rate estimates and keep them consistent. And then, as I said, this requires a big processing system. So those are all of the things that we need to be able to keep doing this. For those who might not be passive microwave remote sensing people, I want to just step back and say a quick little bit about that. So this is a transmittance diagram as a function of frequency from 0 to 300 gigahertz. So we're looking at the microwave spectrum here. And the frequencies I'm going to be talking about and have been talking about are generally in these window channels, so very high transmittance. And the 10, 19, those ones that I'm talking about, they have very high transmittance. So you're seeing through pretty much the entire atmosphere. As we move up, I'll talk about 89, 165. These are still technically window channels, but you can see there is some emission from the atmosphere. So you're going to see a little bit of a difference in the brightness temperatures in those window regions. We have water vapor absorption lines around 21, 22, and 183 that I'll be talking about. Different pieces of information content available there, but I just kind of wanted to give this to you to sort of give you a sense of where in the spectrum we're looking when we talk about these frequencies. These are the things that are going to contribute to the brightness temperatures that we see. So there's a surface emission that depends on the surface emissivity. Over the ocean, it depends on salinity, temperature, wind speed, and foam on the surface. Then from the liquid hydrometeors, you're going to have me scattering and absorption, which again will vary depending on what kind of frequency you're looking at. Cloud water absorption and emission. The melting layer has its own radiative properties that we have to account for. We have frozen hydrometeors. There's scattering associated with those. That gets very complex depending on, what types, what density, what number of ice particles you have. And then you have atmospheric absorption by oxygen and water vapor. Again, in the window channels, that's very small at the lower frequencies, but you do need to account for that, especially the water vapor, as you start talking about the higher frequency window channels like 89. So all of these things have to be accounted for when you're looking at these microwave signals. So if you've ever seen a talk by me, you've probably seen this figure. This is my favorite figure. I love showing it. I think when you're talking about passive microwave precipitation, remote sensing, you could just show this and that would be all you needed to show. So this is a swath, a TMI overpass across South America. And we have some precipitation happening over the ocean in the upper right corner and some over the land that you can see in the 85 down on the bottom. So if we start with the lower frequencies, 10 and 19 gigahertz, the ocean looks very cold. Where we have precipitation happening, you see those liquid hydrometeors are emitting radiation at these frequencies. They look warm. Very easy to distinguish this warm emission signal from the cold ocean background. Over land, there might be an emission signal. It's hard to say. You can't really tell just from looking at it. A little more complicated there. The 21 gigahertz is near that first water vapor absorption line that I mentioned. So you see this really broad signal from the atmosphere associated with the gradient in water vapor there. 37 gigahertz is a really cool channel because you see a really strong emission signal, but you also start to see some scattering from that overland precipitation. You have a little bit of both happening in this channel. This is the favored channel for people who look at tropical cyclones. This is a very valuable one for them. And then at the 85 gigahertz, you're really looking at the scattering signals. So that's how you diagnose your precipitation at this channel. And you'll notice too, the land always looks very, very hot. The emissivity is very high compared to the ocean. So the information content that you're getting from these channels is different over land than it is over ocean. And you can also really see that change in contribution from the atmosphere as you move up in frequency. You're not seeing anything from the atmosphere down at 10. You're just seeing the cold ocean surface. But up at 85, even though it's still a window channel, you can really see that bit of a warm contribution from the atmosphere. So I think this kind of demonstrates everything you need to know about how passive microwave remote sensing for precipitation works. All right, so we need this physically consistent database from the GPM combined retrievals. We do this, we get full physical profiles that are built from those combined retrievals that can be used in the constellation retrievals. This is all described in a paper by Chris Kummerow. And then to map this to all of the other constellation members, which as I mentioned, might have different frequencies, footprint sizes, viewing geometry, we have to do radiative transfer calculations using those physical profiles from the combined retrievals. So this is the radiative transfer equation. I'm not going to derive it or anything, but I just wanted to point out this first term is the surface contribution attenuated by the atmosphere. So you'll see very prominently that emissivity term. This is going to be very important when we start talking about precipitation over land. And then we have the atmospheric contribution. And this emissivity is very difficult to measure. But if you look at this equation, you can see very quickly that if we understand the atmosphere, for example, if it's cloud-free and we have like a sounding that can tell us how temperature and water vapor are changing with height, we can vary. The only unknown left then is the emissivity. So it's pretty easy to retrieve if you understand the atmosphere. Again, we use the Bayesian algorithms now, moving to machine learning. But in all of those, the important thing is the database. The retrieval success is completely dependent on the quality and the representativeness of the a priori database, whether you're doing machine learning or Bayesian or whatever. Over land, as you saw from the South America figure, that emissivity is very large. That was just a snapshot, so you didn't get a chance to see. It's also hugely dynamic. So, some previous precipitation on the surface will make, a huge change. If a farmer harvests their crops, you're going to see a huge change in the emissivity. It's very dynamic and very large, so it's a bit of a tricky parameter. It's mostly dependent in these frequencies on soil moisture, vegetation, temperature, soil texture, but things like dew on the surface will make a huge difference. Difficult to model. But again, fairly simple to retrieve in non-precipitating conditions where we feel like we have a good handle on what's happening in the atmosphere. So I'm going to talk quite a bit here about that challenge of retrieving passive microwave precipitation over land, because that's my favorite thing. So we can actually use that really tricky, highly dynamic emissivity information to help the retrievals. And this is some work I did a couple years ago on a hybrid retrieval with dynamic surface constraints, I called it. So it is a hybrid between, for if there's any NOAA people in here, the MERS retrieval scheme and the Goddard GPROF retrieval scheme. So basically, the first pass you do an optical estimation retrieval similar to what MERS does. I used something that Joe Munchak developed at Goddard. From the OE retrieves emissivity, water vapor, cloud water over the ocean. And you can use the retrieved emissivity, for one thing, to determine where there's snow cover. Obviously, snow cover on the surface has a big impact on the emissivity. And any place that OE works very well when there are no hydrometeors in the atmosphere. So if it converges, you can be pretty certain that there are no hydrometeors. That's a non-raining pixel. If it does not converge, it doesn't necessarily mean that there's precipitation happening. It means that there's something going on in that footprint that the OE can't quite account for. So we assume in any places where that first pass optimal estimation converges that those are precipitation free. Then in those areas where it does not converge, and we decide that based on the normalized error parameter that comes out of the optimal estimation, we just stick GPROF in there basically. So instead of running GPROF over everything where it might not know whether some signal from the surface has to do with precipitation or, it just rained and so there's some water on the surface and so it looks a little bit different. We don't even let GPROF run there. We just stick it in where that OE does not converge. And I mentioned that the operational GPROF uses model information to constrain the retrieval. Here we use retrieved information to constrain the retrieval. So I mentioned the OE retrieves the water vapor. Obviously, you can't use it in the places where it doesn't converge, but what we do is we interpolate that retrieved water vapor over the high chi-squared areas, and we allow the retrieval to look in that bin and bins that are a little bit higher to account for higher water vapor where there's precipitation. And then rather than a static surface database like GPROF uses with surface temperature, we actually use emissivity as the other constraint to the retrieval. And again, we can't use the retrieved emissivity where the algorithm didn't converge, but we go ahead and interpolate over the non-converging areas, and we allow the algorithm to search over that emissivity and also emissivities that are slightly lower to account for the decrease in emissivity from water on the surface from the precipitation. So this hybrid thing, just a little bit of a tweak to GPROF to use more of the information content in the TBs rather than bringing in that model data. And there's an example of that in the figures on the right. So there's the 18 gigahertz TB on the top left and the retrieved emissivity on the right. The normalized error parameters, so these red areas are the areas where the OE did not converge. I put the 89 on the right so you can see the scattering signal is very closely associated with those non-convergent areas. The 183 plus or minus 3 is shown on the bottom left, and the retrieved TPW. So you can see holes in those areas where it didn't converge, and that's where we would interpolate over. And here's an example of how that can help the retrieval. So this is a GMI overpass from September 2015. The upper left here shows MRMS surface radar precipitation. So you can see if we zoom in, as you see on the right, to southern Illinois, no precipitation there from the surface radar or from the DPR KU radar shown in the upper left there. The 89 gigahertz channel is in the middle here, and the 183 plus or minus 3. From the 89, you can see, and actually the 183, there's a bit of a scattering signal over southern Illinois, but no radars are seeing precipitation. So we have some clouds that are scattering. And the TPW that GPROF is using is on the bottom left here, and you can see it's a bit more smoothed than the retrieved TPW on the right, which has some much higher values and is higher resolution. So since these retrievals are both being constrained by the water vapor, the retrievals are looking in different areas of the database because of the different TPWs that they're using. And so GPROF is shown on the upper right, and also the lower right, that's like a modified GPROF, but they're both retrieving precipitation associated with that scattering signal. If we do this hybrid technique, we get 0, no matter what cutoff of the error parameter we use. So some value to this by making sure that the algorithm is not mistaking other signals from clouds or from things on the surface as precipitation, and we get rid of quite a bit of false alarms. So this is a global view for 1 year using that technique. The bottom here is GPROF. These are false alarms. And then the top 3 are different values of cutoff for the error parameter. Obviously, as you crank up that cutoff, you're also going to miss some detection. So we found in this paper that about 0.3 was a really great spot where you decrease a huge amount of half. False alarms are decreased by half. And you don't affect the probability of detection. So we can use that information about how the emissivity is changing using retrieved values to get rid of false alarms in the retrievals. Retrieved emissivity is really valuable because it captures those dynamics. But of course, we have those holes, right, that we were interpolating over. And as I mentioned, when we do the databases, we need to do radiative transfer and calculate a brightness temperature. So we need an emissivity in these areas. We need to have something to put in precipitating conditions. And emissivity can be modeled and it can be retrieved. Each of those techniques have strengths. Modeling basically because it's a bottom-up technique, so it doesn't matter if it's raining or snowing or whatever, you can still calculate it. And then the retrievals because they tend to be more accurate. So we want to see if there's a way we can make the most of both of those pieces of information. So the next thing I'm going to talk about is what I call a semi-empirical model for emissivity estimation. And this is something that I worked on for AMSTER-E, but am currently working on for GMI and for a future NASA hyperspectral instrument. And side note, I'm trying to hire a postdoc to work with this on me. So if you know anyone who might be interested, please get in touch. But basically, it uses a physical model for 10 or 19 gigahertz emissivity. The inputs are soil type, soil moisture, surface temperature, LAI, and antecedent precipitation. So things that aren't too terribly difficult to get on a global scale. We use, for example, the SMAP level 4 soil moisture product. And these lower frequencies, 10 and 19, are where physical models and retrievals agree best, as demonstrated by Essex Zone for our 2012. And I'll show a figure from that paper on the next slide. And then we couple that to an empirical model, which uses information content from the retrievals, covariance relationships between each of the frequencies to map those modeled emissivities to all of the higher frequencies. And that's using a technique developed by Janice, by the way, in 2010, and I'll explain more about that in a bit. So this is from the Ferraro et al. Paper that brought Valco and I into the fold, I think, originally. So this is a plot from that paper. These are plots of emissivity times temperature. So the agreement looks a little artificially better than it would if you were just plotting emissivity. But these are for the Southern Great Plains ARM sites at 10 gigahertz, 19, 37, and 89. And it's basically comparing model emissivity with a few different retrieval techniques. And it's a bit complicated, but I just want you to focus on this orangish, goldish line is the model. And all the colors are mostly different retrieval techniques. And so you see at 10 and 19, all of those lines sort of move together throughout time and they agree reasonably well. However, as we move up in frequency and you're starting to get more of that scattering component, the model really diverges from all of the retrieval techniques. We start to have a lot more disagreement there. And there's been work done trying to figure out why that is. And I think really what it comes down to is that we just don't understand scattering very well. There's still a lot of work to be done in modeling those higher frequencies. So this semi-empirical technique, you start with a pretty simple physical model at 10 or 19 gigahertz. It's kind of a hybrid of the European and American model emissivities. So you've got emission from the soil, and you've got scattering from the vegetation layer and emission, and you just do radiative transfer through that. I also added a component for intercepted water. If there's dew or recent precipitation, that has a big effect on the emissivity as well. And then the empirical model. So this example is for AMSR-E. It uses 5 years of, I cloud cleared all of the pixels with MODIS to be sure they were super cloud free. So we got 2 million pixels to develop these relationships. So these are plots of the emissivity in color as a function of soil moisture on the x-axis and leaf area index on the y-axis. So at the lower frequencies, you can see that the emissivity is much more visibly a function, especially in the H channel up here, of the soil moisture. And as we move up in frequency, it starts to vary much more clearly to the eye here with leaf area index. And that makes sense, right? So in the lower frequencies, we're mainly concerned with that emission from the soil and the soil moisture. And then as we move up, you're getting more of a component of the scattering from that vegetation. So it's more dependent on the vegetation and how you're representing that. So we put that together to develop these relationships, and that's what these lines are. So we do them as a function of soil moisture and vegetation to account for that. So for example, those top 3 plots there are for pixels that have a leaf area index of 3 and a soil moisture of 0.3, and it's showing the relationship between 10H and 3 other frequencies. And you can see that they're pretty decent relationships. It's a decent model. They're pretty straight lines. Just for fun, I also colored them by temperature. That's another, it does seem to separate by that out as well. And then the table in the bottom there just shows that the correlation between the channels is much improved by this binning by quite a bit. So those seem to be the important parameters to account for to create these covariance relationships. And then here's an example of how that works. So this is the Southern Great Plains area in July of 2009. You have this temperature, this leaf area index, soil moisture, and there had been some recent precipitation. So you can actually see the impact of that in the soil moisture on the bottom left there. And these are the computed emissivities. So the 10 is coming from that physical model, and then all of the other frequencies are computed using those covariance relationships. So okay. And so the plots on the right here show the comparison of the simulations that are computed with those modeled emissivities and radiative transfer compared to observations from the AMSR-E satellite. And you can see that particularly at the lower frequencies, they match extremely well. At 89, we have this bit of a tail. I think those are some clouds that did not get knocked out of there by the cloud clearing algorithm. And then just for comparison, this is a figure I made for a paper of Chris's over the ocean. And so it's very similar agreement over the ocean and over the land. Snow is also an important current challenge for these passive microwave algorithms. It's very challenging to measure in the passive microwave, particularly over snow-covered surfaces. You know, we're talking about scattering. And again, as I mentioned, we just don't really understand scattering very well. So these are some plots from Sujay Kumar, who's in our hydrology lab. The hydrologists are using iMerge snow and precipitation to run their land surface models. And so he has a plot here of MODIS snow cover over high mountain Asia. And then on the left are 2 different versions of iMerge. And there are some pretty significant differences between the versions, which is a problem in itself. But you'll also notice that in both versions, it's just missing a lot of that snow that you can see in the MODIS image. So misses are a big problem, especially over mountainous areas. And then if you look at the plot on the right, I got this one from Bill Olson. This is a comparison of the GPM combined snow rate to surface NexRad snow rate. And you can see that the combined is just quite low. This is in Marquette, Michigan. So we have problems with misses. We have problems with underestimation where we are retrieving something. So this isn't just something we can bias correct or calibrate for. This is an issue. We need to understand how the scattering works better to improve these algorithms. We do have a lot of people working on this. People are doing these incredible scattering calculations for complex particles. The piece that we're missing is how we distribute those particles into our profiles. We don't know how many dendrites and how many plates there are in any given column. But I think those things are coming together, and we're going to see big improvements in snow over the next 10 years, I think. Light precipitation has also really been an issue. These are some more figures from Bill on the top. They're zonal mean precipitation plots comparing the combined products to GPCP. And this has been a long known problem that particularly over these high latitude ocean areas, we're missing a lot of precipitation, about 10% in this plot here. And that is because all of these algorithms are using, again, the 2B combined product to calibrate. And the 2B combined product only retrieves precipitation where there's an active radar signal. So if you have light precipitation, such as you often see in the high latitudes, none of the algorithms, GPROF, nothing can retrieve it because they're all calibrating to the Cora. So we're looking at ways to fix this. We have a lot of great ideas. This is something on the bottom that Mircea Grecu and I have been working on using machine learning. So he trained the GMI to estimate Cora precipitation. So he's not actually adding in any information about lighter precipitation, but he's just sort of training what the signals look like for different precipitation rates. And he's showing here just a single overpass where the combined is shown on the left. And when he adds in that light precipitation from the GMI to that combined product, you get a very realistic, I think, picture of the lighter below radar sensitivity precipitation. We have a lot of work to do on this still with validation, et cetera, but I think very promising. This is another place where the next 5 to 10 years, I think you're going to see huge improvements in this light precipitation area. All right, so talking about the constellation now. This is a plot that Chris Kidd made showing the history of the passive microwave constellation. So on the top, we have TRIM and GPM, which are the only true precipitation focused satellites. And then in blue here, he has other imagers, which have that low frequency, emission information. And then we have the sounders in green, which we definitely use. We love it, but different information content. That's the high frequency is you only get the scattering, so more of an indirect relationship to precipitation. So this is kind of where we are. And he made this figure, I think it's incredible, showing that we actually have 47 years of global precipitation products that you can retrieve available. But again, with time, the frequencies that have been used here and the radiometers that were available, the constellation, the character of it has been changing. So you have different information content going into these estimates. And if you're going to use them for any sort of long-term study, it's important to understand that difference. And so that gets us to the topic of channel selection. What's the information from these different channels? And so to look at that, I ran a year of GPROF retrievals using different subsets of the channels from the GMI. So here I'm showing Hurricane Ida, and full retrieval on the top is using all 13 channels. For reference, I've got the 10V and 166V channels plotted on the right. Low is 10 through 37 gigahertz, so just the emission information really. High is 89 to 183, and high 2 is 165 to 183. And you can see that when we have that low frequency information, you get all of this high value precipitation associated with the center of the storm. As you start taking that information away and you're just dealing with the scattering, and you can kind of get an insight to this by looking at the 10. So this is the emission signal. This is where the liquid rain is, where the full is seeing high precipitation values. But the scattering, the cloud shield associated with the storm is looks more like this in the 166. And if you only use those high frequency channels, then you just basically get precipitation associated with that scattering, which in many cases isn't actually even there according to the lower frequencies. So you're really seeing a different picture of this storm depending on what frequencies you're looking at it with. So when we talk about these products over time, there's effect on the product continuity of the different spectral availability because you're changing what you're actually measuring. So we need consistent measurements and consistent information content for this to work. These are zonal mean plots from that same experiment. If you look at the plot on the left, the black line is the full retrieval using all 13 channels. The blues are using the lower frequencies and the green and orange are higher frequencies. So over the ocean, we see really what we would expect. As you start taking away frequencies, you retrieve less precipitation and you get the least amount when you use only those high frequency channels. So you only have the scattering information available. And if you can see that on the map, on the right, with those lower frequencies, you've got mostly blues. But as we start looking at the higher frequencies, it actually gets really noisy and complicated over land in particular, but even over the ocean as well. So again, this is not a situation where we can just correct for the loss of a frequency with a bias correction or a calibration. This is complicated and something that we need the information content to be able to do these measurements. Looking out into the future, as I said, GPM will be done in the early 2030s. A lot of the character of the constellation, particularly the imagers, is changing at the same time. We have our Japanese and European colleagues that are continuing these imagers. We have AMSR 3 and the MWIs from Europe. We also have a lot of change in things like AOS, Tropics, and the Tomorrow.io commercial constellation, where we're seeing a move in a lot of these missions to smaller, cheaper, higher frequency instruments. And so from everything I've just said, I hope that that immediately makes you think that will change the character of what we're measuring. That gives us that scattering-based, indirect look at precipitation, and it will change the estimates that we get. Just a quick word about oversampling and resolution enhancements, because I hope I've convinced you that those lower frequencies are extremely valuable. But of course, they're the expensive ones, right? We need a big antenna to be able to have those at any kind of useful resolution. And so we're working on ideas of how we could make that more affordable and more attractive to people like Tomorrow.io and NOAA, the operational agencies, that maybe they would be willing to fly more of these. And so Merchant and I have been looking at oversampling as a way to enhance the resolution with a cheaper radiometer with a smaller antenna. So this is from some experiments that we've been doing. He made a simulated 4-kilometer brightness temperature field, convolved it into GMI footprints, and then used machine learning and other deconvolution models to sort of map that back to a higher frequency observation. And it looks actually extremely promising. The correlations improve quite a bit. The RMSs go down. There does seem to be a limit to it. We can't use this to get like 1-kilometer resolution, but it's looking really good. And we actually have a scientist at Marshall who's using these deconvolved TBs to try and get a better look at hail signatures at 19 gigahertz. We can give her 5-kilometer resolution from the GMI because it turns out that the 10 and 19 of GMI actually oversample a bit. It's information we generally throw away, but it's there. So this is an exciting area as well. This is just my summary. We've had a decade of the GPM mission and these amazing, consistent global precipitation products that I really think have changed the game. We've got some challenges, but there's a lot of exciting work happening, and I think we're going to see improvements in a lot of these areas very soon. This global mapping is extremely important for a lot of applications. And as we start to have it for longer, I think has implications for the climate data record. But as we're moving to these smaller, cheaper, higher frequency radiometers, we lose important direct precipitation information. And using GPM in the inclined orbit with these frequencies, we lose that calibration factor, which is what makes these consistent retrievals and I think makes the product the most valuable. It'll affect the character of any of these multi-satellite precipitation products. I think oversampling shows some promise to make some of these more affordable small sats more valuable through this empirical resolution enhancement. But for any future efforts, calibration and processing are really key components. And sort of the thesis statement is to make these amazing products that we all use, we need to get the data. It has to be the right data. We have to process the data. We have to archive the data because we reprocess the entire record every time we figured out we can do something better. And all of this is necessary for robust science and applications. That's it.
Thank you so much, Sarah. We have several online questions. We will go with the online questions.
Oh, yeah. Oh, okay. Okay, the first question is cell phone signals a potential source of contamination or a non-issue? Could it become an issue?
It could certainly become an issue at the moment. So the microwave bands, this is a little bit out of my area, but they're very highly protected. There are definitely some issues with some of the channels that we've been using are getting sold off for commercial applications, and we have these RFI issues. I think, you know, these upcoming hyperspectral missions, part of their aim is to try and deal with some of that RFI issue. I don't know of anything particular with cell phones that any. Yeah, you probably know more about it than I do.
So the 5G network is infringing upon that 22, 23 gigahertz band. So that,
Gotcha.
we'll see, I was actually going to ask a similar question if you noticed anything with that. I was involved several years ago, you know, with a group from NASA and NOAA, went to the White House, who basically told us, this is what we're doing. Thanks for coming, just so we can write a report to say that you guys were here and voiced your opinions. But so that, yeah, we'll see. And I think more and more of these protected bands, you know, are going to get auctioned off. And then there's a whole commission that, you know, tries to protect these things. But
Right. You get the leakage too, like Chris talks about the one with the garage door openers that somebody was using that were leaking into protected bands.
right,
And
right.
yeah.
So yeah, we'll see.
Yeah.
It depends on how much power they put out. And
Yep.
I think that initially, right.
Yeah. Yeah.
Yeah.
Yeah. Well, I'm sure it does. Yeah. 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 I know there are people that put a lot of time into finding those RFI contaminated signals and kicking them out of the algorithms.
Yeah, I mean, ages ago, but Bob might remember this. Don't be insulted that I said ages ago. But some of the original microwave sensors, I think at 6 gigahertz, they would see like submarine transmissions.
Yeah.
There was something in one of the like the grocery store tabloids back when they had them, showed like there was some secret Martian colony under Antarctica or something. People were making all sorts of things. But anyway.
Secret Martians screwing up our precipitation estimates for decades.
Okay, the next question is two-part. So first, do you find significant changes in accuracy by region? Are regions with more gauges more accurate?
Ooh, that's a great question. The first part of the question, absolutely. There are huge differences with regions. I mentioned some areas that we really struggle with, such as mountains. That's a really tough problem. The accuracy is not as good there. We've been working with a gentleman in New Zealand who's been comparing iMerge estimates with his surface radar estimates. And so there you have mountains and coast. Coast is another big, very difficult area for the passive microwave. So that's a region that's quite difficult. And so you talk about gauges. The gauge adjustments are done on, I think, a monthly basis. So it's, the gauges don't nudge a particular observation in a particular direction. And so this New Zealand study was noticing that sometimes the gauge adjustments were moving things in the wrong direction for particular instantaneous precipitation events. So I think the gauges really help on if you're looking at a climate scale, if you're looking at like monthly mean precipitation, but if you're looking at a specific weather event, you're not going to see a lot of improvement from that.
And the next part is there a limit to spatial resolution for such data sets?
Yeah, definitely. Resolution is expensive. Again, it's those big antennas. So I think the limit of what we're seeing now from a lot of the brightness temperatures is 4 to 5 kilometers currently. Now that might improve in the future. I don't know where technology is going. I'm not an engineer, but 4 to 5 kilometers is about the limit right now.
Yeah, I got a question about the low frequency imagers. Since Cube CNC don't have the low frequencies, so have you taken a look at the like sensitivity test over land compared to over the ocean? Does the low frequency channels play a big role for the over land retrieval?
So when we just look at comparisons, the land, you don't see as much of a degradation losing that emission signal because we don't use it. But if the algorithm, that is a function of how the algorithms work right now. If you were to incorporate something like the dynamic retrieval that I showed, where you're using the low frequencies to get rid of false alarms, then you would see an impact from that. But I think because we understand so little about the surface emissivity and we kind of let the algorithm reduce to scattering relationships over land, you're not going to see so much degradation over land in using the high frequencies rather than losing the imagers. Yeah.
Any other questions?
Yeah, very exciting talk. I teach remote sensing class, and rainfall is a major topic. And every year I try to update something. Apparently, benefit from yours. I'll change some slide next year.
Excellent.
I hope you can share your slide with.
Absolutely. Happy to.
I have first question still related to my very first question. Your image data set has every half hour.
Yeah.
But if you look at your satellite sensors, they are really just those microwave radiometer and of course radar included. And they are mostly polar optic satellite, and they are by far not every half hour.
Right.
So how do you fill the gap?
They're using geostationary data to
So you
fill the
do
gap.
use
Yes. Yes.
right?
Yep.
Okay.
Yep.
That's a very important question.
Yes.
Okay, and secondly, there have been so many, rainfall products, and there have also been many merged products.
Yes.
So I hope this product is the best represent all in the past, but I do want to know what actual gain except the GPM sensor itself. Prior to the GPM, there has been many other products, but during the GPM, is this the most integrated product by merging all possible source of information from, rain gauge, geostationary, polar orbiting, passive, active, microwave, optical, all sensors involved in this product?
JAXA has a very similar product called GS-MAP
Mhm.
that's using basically the same information.
Mhm.
I don't know what all GPCP and some of the other merged products use, but I mean, as far as I know, iMerge is pretty state of the art as far as integrating all of that information
Mhm.
and the 0.1 degree every 30 minutes.
Okay, and for the optical sensor, light rain has been a major problem. The drizzle, the light rain from the warm cloud, those low-level cloud.
Yeah.
That's, emissivity not so much, emission not so much from the ground, while reflection is also, not so strong. So I wonder if you use optical remote sensing. For example, our own group developed a method to use the microphysics information. The cloud particle size change with height is a good source of information to infer if there is warm rain or not. I wonder, how do you deal with the warm rain for the low-level cloud?
So from the passive microwave, we can only retrieve warm rain over the ocean. So we would look for that emission signal in the lower frequencies.
Mm.
It would actually be really interesting to compare with your your information on the microphysics to sort of see. Right now, over the land, we have no way actually of retrieving warm rain. It's just mist.
Okay, so that
yeah.
we can certainly try to collaborate. And
Absolutely.
also, it doesn't matter whether it's land, ocean.
Yeah,
Principle is the same.
yeah, absolutely. Yeah.
Okay, good. Thank you.
Love to hear more about that.
Of the precipitation, detection program. So there's a lot of new stuff, proposed from the commercial satellites, such as, like put the passive and active sensors together in a satellite, in one satellite, and leverage the AI, like the passive to detect the cloud, and then, let there is cloud, then let the active sensors then chip in.
Yeah, yeah.
So that's a very good idea. We hear a lot of this talk, some of this talk in the different conferences.
That's cool. That's like the hardware version of my hybrid retrieval.
Right,
Yeah.
exactly.
Yeah.
So just wondering, for the GPM, NASA's GPM plan, do you have any updates in the future about the instrument? Like, do you want to keep the same, or do you want, you have plan to add more channels, like at the 50 and 118 temperature sounding channels into GPM, like the next generation of European macro imager, like that? And for the satellite, do you still want to keep just US have the one core satellite with the passive, and Japan have been keep maintaining the DPR? Do you have any change for the current satellite orbit?
So unfortunately, there's no plan at NASA to do any sort of GPM follow-on.
Oh,
Yeah, we do have the AOS mission coming up, and that will involve a JAXA KU radar in an inclined orbit. And there will be a French-flown high-frequency radiometer associated with that. So sort of two of the components. There are no plans currently for the lower frequencies or any kind of imager to fly with that. As I mentioned, JAXA is doing an AMSR 3 and the Europeans are doing the MWIs. So there will be imager data out there. But for the moment anyway, NASA doesn't have any plans to.
oh, okay, that is the, because I think GMI is only very high quality passive macro imager.
Yeah.
Like, because NOAA don't have imager.
Right.
So the NASA, this GMI almost like operational, is operational.
Absolutely. I mean, I think a lot of the world does consider it operational. And as I said, it's key to the calibration of this entire constellation. So I'm working on some white papers for the next decadal survey focused on this. So if you want to join in, please contact me and we'd love to have you aboard.
Good luck.
Thanks.
Other questions? If not, let's give one more applause to the speaker. And we will have two more in-person seminars and several more virtual ones, so stay tuned. Thank you so much.